So we talked about the images and pre-images last time. Not a very complicated topic, If you consider, especially if you consider functions as sets of all the pairs, everything becomes pretty straight. And we did some examples last time. We just have a little bit more in this section and actually in this unit. So let's just finish this section first. We're talking about images, but we have not discussed the pre-image. But it's pretty much the same idea, and you probably know what it is. So what's the definition of pre-image? So let's just start from function f from set A to set B, and just pick up a subset of the codomain B. We call it T, and then you just find all the elements in the domain that map to T. Okay. So you just look at it, all the elements in this subset T of B, and then find the pre-image of each of those and put them together. So that makes the pre-image of a set. Okay. So obviously, because you are considering elements in the domain or part of it, so the pre-image of a set from the codomain is a subset of a domain, obviously. Okay. So one thing to be cautious when you use the notation of f, -1 here, or inverse. Do not confuse it with the inverse functions. We're not talking about the inverse function. This is for any function. You can find the pre-image of a subset of a codomain for any function, right? By definition. But for inverse functions, then they only exist for bijective functions. You cannot talk about functions not bijective. Okay, so that's different. So they share the different. They share the same notation, but the meaning is quite different in each case. But we are using the same kind of similar notation, but with the argument in here, one is set and the other is element, to distinguish between these two things. So when the argument is set, it automatically means the pre-image. When the argument is element, it automatically means that's an inverse function. Okay. Just be careful. Okay, so let's just do one example here. We have two sets, A and B. Set A has 5 numbers, 1 to 5, and set B has 4 numbers, 6 to 9. And let's just define a function from A to B by pairing, numbers in A by numbers in B. So we got 1, 2, 3, 5 other pairs, of course, because each number in set A needs to be paired with some number in set B by definition to make a function. Okay. So, but you can see, this is all the pairs. You don't have to pair all the numbers in set B in the codomain. Like 8 does not appear in any of other pairs in the second coordinate, right? So that's pretty fine for function. So then, since we are talking about pre-images of sets, then you can pick up any subset of the codomain B and try to find the pre-image under F. of that. For example, if I just pick up the subset with two numbers, 6 and 7 of B, and then you can find the pre-image of each of the elements in this subset of B and put them together. That will give you the pre-image of the subset. All right, like 6. So we know 2, 4 are paired with 6. So that will include 2 and 4 as elements of the pre-image, and the number 7 is paired with 1 and 3 in the second coordinate. So pre-image of 7 includes 1 and 3. So then the pre-image of the subset includes all the pre-image of all the elements in the subset. So that includes 1, 2, 3, and 4, right? 2, 4, 1, 3, right? Okay, so that's the pre-image of the subset of B. It is a subset of A, of course. That's why I can include 5. Okay, so it is a proper subset of A. How about the pre-image of the subset with 1 element 8 of B? So that's a subset of B, obviously, but you cannot find any other pair in this function with 8 as second coordinate. So the pre-image is empty. There's no other pair in this function with 8 as the second coordinate, right? And how about the pre-image of the set with number 9 only? You can see there's only one other pair in the function. Always consider the function as other pairs. So the only pair is 5 from set A. So the pre-image of that is just set of one number, 5. Okay. Once again, when you talk about pre-image of a subset of codomain, it gives you a subset of the domain. So you should always write the answer in set notation. So that's why you need parentheses. If you just put a 5 in here without parentheses, that's not right. You should write in sets, okay? The last one is a subset of B again. It includes 3 numbers, 7, 8, and 9. So if you just look at 7, 8, or 9, the second coordinate in F, and you see 1, 3, and 9. I mean 5, and 5, 1, 3, 5. Okay, and 8 does not have 3 images, so that just includes 3 numbers. So that's the set of 3 numbers, 1, 3, and 5. Okay. So you can pick up any other subsets of B, the codomain, and try to find the pre-images. We just listed a few of them, but you can do more than that, of course, and you can find all the subsets of B and try to find the pre-image of each. So the question is, how many subsets of A are pre-images of sets of B? So the question is, how many pre-images can you find, in this function? Okay. It turns out, if you think about it, 8 is not in the range of this function, right? So you can basically rule out the number 8 in all the subsets, because that will each subset of the codomain B, including 8, will give you this same answer when you try to find the pre-image. We'll give you the same result as the other subset when you taking out the 8. So they give you identical results. So it really doesn't matter whether you include 8 in the subset of B or not, right? Because they will give you the same pre-image. So then considering that, you only need to consider 3 numbers. Okay. So the question is how many subsets the set 6, 7, 9 that can give. And then of course for those 3 numbers you can always find pre-image in the domain. So if you rule out 8 in all the subsets of B, then how many possibilities you have? You have 8. Okay. For each of those 6, 8, or 9, if you consider a subset of B with different number of numbers, you can either include the 6 or not. So that gives you 2 possibilities, and you can also consider 8 in the same way. Either the subset includes 8 or not, and same for 9. So you can include 9 or not. So that's another 2 options. So in total, you just multiply them together, you get, these are independent events as we are going to talk about them probability. So in total, you're going to get the 8 different subsets of B. And each of those subsets will result in a different pre-image in A. So in total, actually, there are 8 subsets of A that are pre-images of subsets of B, and you can actually list those subsets of A pretty easily. All right, and that also include the empty set, but we know the pre-image of the empty set is also the empty set, right? You don't have anything to map in, or you cannot find anything to map to empty set. Okay, so that includes the pre-image of the set of 8. Okay, so you don't have to count this pre-image of the set of 8 again. It always includes in those 8 size 8 subsets of A. All right. So that's this example. Any questions?
Not for me.
All right. If not, then let's just do one more example. Then we're done with this section. So let's just define that function. We know this function. That's the quadratic function or parabola. Fx equals x squared from R to R. So if you try to find the pre-image of the set of one number x, where x is positive, then you're gonna get two pre-images. If you try to solve the the equation, x squared equal to a positive number, you get 2 solutions. So the square root of negative x and negative square root of x. So that's the pre-image of this set. It includes 2 numbers, a set. Of course, if x is negative, then you will not be able to find the square root in real numbers. So in that case, the pre-image of that set of a negative number is empty. Okay. And finally, if x equals to 0, then you can only find the one solution. If you try to solve x squared equal to 0, you get x equal to 0. So you only get one number in the pre-image of the set of 0. Okay, so pretty straight. So we're done with this section, and we're done with this unit. I think this section is relatively easy. Not too much, not many things that are abstract or a lot of definition and so. Mm. So, any questions for this unit?
No.
Okay, great. So, uh, we're gonna continue to the next unit, which is the last unit of this course, probability theory. Okay, that'll be interesting. So let me just close this and open the section for probability. Okay, let me see. I think I'm going to stop the share first and then share it back. Can everybody see the slide?
Yes.
Okay, so in this unit, we're going to talk about a completely different thing. This is a course for a survey of advanced course, math course or something. So we just discuss some different topics. Like we talk about sets, we talk about logic, we talk about functions, and now we're going to talk about the basic probability concepts. Okay, so this is a completely different area, but it's very interesting subject. I hope you can see the difference, between this and other things. Probability is more like applied math, but the concepts are still built upon pure math in sets, especially when we try to define probability in rigorous way. We do need pure math. All right. So in the first section, we're going to start from the definition of the probability. How do we define the probability of an event rigorously mathematically? All right. So originally, the probability theory is from or was from the games, of chance. You want to, if you have ever had a chance or experiences to play a game you want to gambling, right? That's just basically a probability game. Okay. Well, for example, if you're talking about unbiased coin and you toss it independently many times or n times, okay, and you know, it only makes sense when you do the experiment many times. So and it will be pretty large, and the relative frequency of hairs, or the ratio of number of hairs to the total number of tosses, is pretty much like a 1/2 or close, right? We are talking about unbiased coin. Another example is a card is drawn from a perfectly shuffled deck and then replace the back, put the back, and then reshuffle again. if you repeat this process again and again, so the question is, what's the frequency, relative frequency of space or any other colors? It will be pretty close to 1/4. All right, there are only four colors, so you get 25% of chance to get a spade. But all of these experiments have to be done in repeated a lot of times. You can also think of 52 possible outcomes in the deck, and if you pick up a single card, there are 13 space, right? And so each time you may get a different color and different number, on the card, but eventually, if you do the experiment enough times, you just divide the number of favorable outcomes, or 13 space to the total number of outcomes, so which is 13 or 52 or 1/4, and we are we exclude those two spatial cards, So that's the original definition, classical definition of probability. It's defined based on the experiments. You have to do a lot of experiments, and you can define the probability. Okay, so the probability of an event is the number of outcomes favorable to the event. That's what you're asking for, divided by the total number of outcomes, where all outcomes are equally likely. Okay, so this definition is based on experiments. It's not a strict mathematical definition. All right. So you cannot, the fact you cannot do the experiments infinite many times, no matter how large the number is. So that's not rigorous mathematically, And another problem is when you define the probability, you assume when you toss the coin, you assume the head and tail appears, equally likely or equal probable. So that's a kind of circular definition. So using the concept of probability to define probability itself, it's not the restricted again. It's not the rigorous mathematical again. So we cannot use this idea as of experiments as the basis of a mathematical theory of probability. All right. Although you can still get some correct results and a lot of conclusions, the mathematical basis is not good. All right. And this also is true, if you use a frequency definition of probability, like the card experiment as we did. So let's say S sub n is the number of occurrences of an event in n independent performances of experiment. So the relative frequency is just the ratio of S sub n over n. Okay, so S sub n is the outcome you want, and is the total outcome. So when n is sufficiently large, Sn will be large too. So you take the limit of this ratio and it should converge to a limit. We talk about we learned a limit before, but it's not always the case. That's not always the true. In the case of tossing an unbiased coin, so you expect this ratio to be 1/2 if you think or consider S sub n as the occurrence of head from the total number of time, tossing. But it may not be unbiased. So in that case, you may get this limit to be 1 or any other number. So like in the gambling, if somebody violates the rule, they can make the outcome favorable to his outcome, to his result. So that may be, greater than half or less than half, or sometimes even you cannot get a limit at all. Okay, so in theory. So again, this definition, based on the experiments, it's not acceptable mathematically. It's not acceptable. Okay, so what would be a good definition, a good starting point to define probability itself, to build a mathematical theory of probability? We want to be perfect. Okay, everything should be strict mathematically. We're going to start from definition from the set, as we call it, sample space. So the sample space is set that includes all the outcomes of an experiment. All right, so the collection of possible outcomes of a random experiment. So that's called the sample space. So it includes all the outcomes. So for example, if a coin is tossed once, we may take this omega, we call using omega as the notation with this sample space. So it's a set that includes all the outcomes. So when you try to toss the coin, you either get head or a tail. So you don't get anything else. So the sample space of this experiment is the set of two outcomes, H and T. Okay, so H represent the head and T the tail. All right. So so that's the case when you toss the coin once, the outcome will be either head or tail. But if you toss it twice, then you consider these two tossing as one experiment. Then one outcome will include, two letters. Okay, each represent the outcome from individual tossing. All right. So this time the sample space omega will be different. It will include 4 elements. All right. HH means you get head in the first tossing and also head in the second tossing. HT means you get head in the first try and the tail in the second try. And TH means you get tail in the first try and head in the second try. And TT means you get the tail in both tries. But each element includes a series of 2 tries. So that's just one element in this set. All right. So when you think about the outcome of of twice tossing, then you have to include all the outcomes of individual try, right? So it includes two outcomes for each element. All right. So one performance of the experiment that correspond to two tosses of the coin. All right. I guess we just stop here. We still have quite a bit to finish this section, and we don't have time anymore. I just put the two sections in together in here, introduction and the next section, because section 2 is these two sections are pretty short. Anyway, any questions about this? I think we have not done too much about the probability, so everything should be easy. Okay.